Hello everyone, welcome to my talk. My name is Minghao Xie. I am a computer engineering PhD student from UC Santa Cruz. Today I'm going to introduce our most recent system prototype named ReFlex4ARM that can support 100G flash storage disaggregation on an ARM SoC. Our motivations start from the observation of recent trends that modern flash devices are becoming more and more powerful. For instance, one SSD can support 500 kilo read IOPS with average latency around 100 microseconds. So we can hardly find an application with full utilization in data centers, especially they are located in the same machine. A more flexible choice would be building a disaggregation system that enables cross-network flash sharing. However, only combining existing library is way less than enough. Suppose we need 3 million IOPS of 4K random read. The traditional Linux storage library called libaio and the traditional networking library called libevent can together only deliver 75 kilo IOPS per core. With this solution, we might need more than 40 cores to achieve our goal. Therefore, we propose a more practical solution that can address all the above issues by jointly designing a system with considerations of both software and hardware. We selected the high-performance disaggregation framework called ReFlex that fuses network and storage stack and delivers up to 850 kilo IOPS per Xeon core. The need mentioned above can be easily satisfied by only using 4 cores. In hardware, we turn to the ARM option that has lower power consumption but still leverage the ReFlex performance with lower budget. This picture shows Broadcom Stingray SoC that we selected. It has a powerful octal ARM core that runs at 3 GHz with a 100G Ethernet port. With this general-purpose ARM CPU, we can run a compact Linux system on it. This smartly can act as a root complex to control an independent storage system without involvement of the host system. Our proposed system will be running like this. There will be a ReFlex4ARM server running on the SmartNIC, hosting a bunch of storage devices as a disaggregated target. Any compute server can access this remote storage over the existing TCP IP-based data center network without significant overhead. By gathering high-performance flash devices in a centralized location, we can get higher flexibility and resolve the issues of resource underutilization. Running on the traditional networking infrastructure also eliminates the need of upgrading existing hardware as well as the software. But what are the challenges are? The weakness of low-power ARM cores deliver lower IOPS and higher latency. What's more, all the old architecture-specific optimization will become invalid with the ARM CPU, and the system needs to be tuned to adapt better networking port. Lastly, the cost efficiency is hard to guarantee with the new hardware without thorough consideration. Our ReFlex4ARM has 3 major designs. Firstly, we extended the original ReFlex implementation with ARM support, and updated storage library SPDK and networking library DPDK to more recent versions with backward compatibility that can enable much faster adoption. We also optimize the system on the critical paths at both C language level and ARM assembly language level. We tuned the system to be able to run on the 100G system instead of the old Reflex with only 10G NICs. Thirdly, we designed the whole system with the ultimate goal of minimizing the total cost of ownership, and made a comparison with the old Reflex, as well as the state-of-the-art system available in the market. For sure, we have other implementations that support future works, like how are we gonna support more storage devices to add more IOPS and more capacity? And how can we configure Flow SLO to suit users' requirements? We've also upgraded the block device driver to remove the need of upgrading up-level software. You may find more details in our submitted abstract. Let's go to the performance evaluations. We conducted our experiments with a client and a Stingray NIC that is connected with 4 SSDs and running a ReFlex4ARM server as the target. The left-hand side figure shows our recent results of latency distribution given increasing throughput. This figure tells us ReFlex4ARM can provide stable latency before reaching the bottleneck, and can enforce a 95% tail latency of less than 400 microseconds at 1.3 million IOPS. On the right-hand side, we evaluated the performance scaling of our system. We can find that ReFlex4ARM can easily saturate the 4 SSD system by only using 4 cores. Utilizing all 8 cores improves the performance for 4K requests, reaching the maximum IOPS rate of our 4 SSDs. In terms of the total cost of ownership, we choose the similar system in the market called LightOS. This system opts to the traditional Xeon-based server, which can deliver 5 million IOPS with 24 SSDs. However, it does come with worse space and power footprint. We adopted the same cost model to perform fair comparison. We can see that ReFlex4ARM is better than the LightOS in both OPEX and KPEX. When running both systems in a 10-year basis, our solution beats the LightOS by 2.6 times on TCO. Another comparison result, which is not plotted here, is that we outperform the original Reflex implementation by an increase of 1.57 times I/O operations at the same cost. In summary, we designed and implemented the ReFlex4ARM, a TCO-optimized cross-platform flash disaggregation solution. It combines a 100 gigabits per second NIC with low-cost ARM processors and NVMe storage interfaces, with providing remote access to flash at 2 million IOPS with sub-100 microsecond access latency. And we designed and implemented a lot of new features to enable more opportunities in data center clusters. We've already open sourced our code at GitHub. You may find our source code in this link. Thank you for listening my talk. I am happy to accept any further questions.
We will not be taking any questions.
Should I put my answer in the chat box or?
Thanks to all our participants for joining us today. This concludes our webcast. You may now disconnect. Have a great day.
You too.